Woohoo!
Yay!
Oh my gosh, is it finally over?
Why are you wearing that ridiculous hat?
It's party time, man. You can't keep your hat on anyways.
I know.
My gosh, I got my goggles
This
on.
is it.
We're
done. This is the last
podcast of the year.
Woohoo!
So we're going to talk about actually kind of a serious topic, though. It's kind of a downer. Nuclear chemistry.
Oh.
Yeah, and all the energies and stuff like that. And like we're going to finish. You know what we finished the whole year with?
How to build a bomb?
Yeah, how to build a nuclear bomb.
Yeah, I'm
so
pretty
it's just really this really exciting topic.
Yeah.
How to build a nuclear bomb. Now, don't any of you go out and build a nuclear bomb. If you go out and build a nuclear bomb, I'll get really mad at you. Okay? And Mr. Sam's, he'll come get you.
Yeah.
If he's still alive. So. Okay. So
But we do need to talk about the science behind it.
Yeah, the science behind it. Actually, we won't give you enough information to actually build a nuclear bomb. That's good.
Yeah.
Because in case this gets out on the internet, which it probably will. So we'll talk. All right, let's do it. Okay, so today what we want to do is do nuclear reactions, and so balancing and the kinetics. So just real fast. Hey, nuclear reactions. Actually, let's back up. Nuclear reactions are about what part of the atom we're going to study.
The nucleus.
And see, the nucleus can do various and a sundry different thing. And what do you find in the nucleus, Mr. Sams?
Protons and neutrons.
So the protons and neutrons can the thing that's interesting about the nucleus of the atom, that's the center of the atom with its protons and its neutrons. Mm-hmm. It can undergo changes. Now, the reality is before today, the last podcast of the year, in this course, chemistry, we really have been really studying how electrons play a role, because that's how makes chemical reactions take place.
Yeah.
But in a nuclear reaction, the nucleus will do something. It will either split up or join, basically, and that's the two options. Now, that leads us to kind of an interesting diagram. This is the nuclear stability diagram. Now let's kind of talk about a couple of things here. This is Z. Now what's Z stand for?
Z is our number of protons.
That's the protons. And N is the number of neutrons. And as it turns out, the higher, if you were to take a line, the early elements, so like hydrogen, hydrogen actually has 1 proton and 0 neutrons. Mm-hmm. But if you take, say, helium, he's got 2 protons and 2 neutrons. So it's got a ratio of 1 to 1.
Yeah, those little elements like to be 1 to 1. Nice and stable.
But as you get higher and higher, so if we take, say, element 80 right here, the nucleus or the nuclei that are stable actually have more neutrons than they do protons.
Right.
And so
Not too many more.
They call that there the zone of stability. These are where you have stable nuclei. Now, and they're called, actually, a fancy word, they're called isotopes of each other. We talked about isomers last times. Yeah. An isotope.
Isopopes.
Isotope. Man, I cannot spell today for life like I ever could. Isotopes. What's an isotope?
Same number of protons, different number of neutrons.
Yeah, and I think we'll talk about that. So I'd write here, the same number of protons, but different number of neutrons. That little, everybody know what that means? This is number. Neutrons. N-E-U-T-R-O-N-S.
N-E-U-R-T-O-N-S. Wow.
I'm having the last podcast. I'm having difficulty.
Not to mention this is the 4th one we've made in a row.
Yeah, you notice our clothing, it's the same.
Yeah.
All right, so in nuclear stability there are actually several types of particles, and actually if you're trying to understand this just for the AP test, this is it. If you understand this, you're good. What's an alpha particle?
Alpha particle is actually just like a helium nucleus. It has 2 protons and 2 neutrons. It actually has a +2 charge on it as well.
Technically, it has a +2 charge, but nuclear people don't care about the charges.
No, because they don't care about electrons.
They don't care about electrons. No. Technically, it has a +2 charge. So it's just 2 protons and 2 neutrons in the nucleus of...
Yeah, now why'd you put that little 4 up there, Mr. Bergman? What is that?
Oh, yeah, the 4 is the weight. This is the atomic weight. Actually, a better thing would be the mass number. They're sort of the same. Actually, it's not really the same. No. It's the mass number, and then number 2 right here is the
number of protons.
Atomic number. Okay.
So if we know the atomic number and we know the mass number, we can always find the neutrons by subtracting them.
Yeah, 4 minus 2, 2.
Yep.
Okay. Now, a beta particle is actually an electron.
It is.
And
it's a nuclear electron.
This is the symbol for a beta particle, or sometimes we actually use the beta symbol, 0 and -1. Now, electrons have no weight or no mass. They have a very small mass, but for this purposes, it's 0. And the charge is -1 of an electron. So that's how you write this. And sometimes you put a E, sometimes you put a B. And a positron is actually a positively charged electron. I'll bet you didn't know that they Yeah, and so these actually exist as well. So it's, again, it has no weight, but its charge is positive. It's a positively charged electron.
And the cool thing is if a positron
meets an electron,
they annihilate each other. It's called nuclear annihilation.
It's
it
very
ceases
cool.
ceases to be matter.
Turns into energy.
Turns into energy.
Lots of energy.
Yeah.
There's also gamma particles. That's
not
symbol
really a particle.
Y.
It's kind
yeah,
of a misnomer.
Probably a gamma
Ray is usually
ray.
what they're called.
And actually, it's just 0, 0. It's just energy.
Yep.
Yeah. A neutron has a weight of 1, and there's no charge, so it's just 1, 0 with an N. That's pretty easy. A proton is a 1, 1 P, or sometimes it's just a 1, 1 H, because if you think about it for a moment, a hydrogen atom has 1 proton, no neutrons, and actually, technically it's got a positive charge, but we don't care about that. A proton is just, so yeah, it's 1, 1. So it's important, if you just memorize, this would be great stuff for like note cards at the end of the year, you just need to write down and memorize all these different particles. And once you know the particles, everything is hinky-dory. All right, now, when they decay, there's different kinds of radioactive activity, and there's what we call radioactive decay. There's beta particle production, positron production, electron capture, alpha particle production, gamma ray production, and spontaneous fission. All right, so we'll just do some examples. Okay, now what is beta particle production?
Okay.
Actually, let's actually take a reaction. Let's take the one they've got here.
Yeah.
Actinium-227-89. I lost my pen. Actinium-227, what was the number?
89.
89. And it makes a beta particle. That's
right.
a 0, -1. Put an E there. And the other thing that it makes, actually, we haven't really talked about this, but when you balance a nuclear reaction, you don't balance it in the way we've balanced other equations.
Just make the numbers add up.
So this is 227, and this needs to be over here. The chemical you're missing needs to have 227, because 227 plus 0 is 227.
Mm-hmm.
And then 89, I need to have this side add up to 89. So 89 plus what? -1 plus what is 89?
90.
It'd be 90. And then I look on my periodic table, and I find element number 90, and that
90
is
TH.
TH. Now, it didn't change its weight, but it went up in its charge. What's up? Or its in its atomic number?
Yeah. The weird thing is we didn't really add any protons. What we did is we turned a neutron into a proton.
Yeah. See, it turned into this plus 0, -1.
So what happened is one of those neutrons kicked out an electron
Split up.
from itself and turned into a proton.
So you probably didn't know this, but a neutron is actually made up of a proton and an electron. In fact, neutrons have a slightly higher mass than do a proton, because they have an electron. It's not really like they have an electron in it. It's not like it's like a shell.
It's
and
not
it's sort of
separate
somehow,
entity.
but when it breaks apart, the neutron. It breaks apart into a proton and an electron.
Now the opposite can also happen. It's called electron capture.
Yes, so it can go both directions.
Yeah.
All right. Actually, let's learn how to balance those reactions. We already talked about it. Tops
So
have to
easy,
add up.
guys. So easy.
Bottoms have to
It's
add
the
up.
easiest thing you'll do all year.
6 plus 2 is 8.
8.
4 plus, I think it'd be 4.
4.
Yeah. This is 3 plus 1 is 4. So 2 plus
2.
2. Now, by the way, now we have to get a periodic table.
Yep.
So it's 4, 2. Let's look at a periodic table. Element number 2 on the periodic table would be helium, wouldn't it?
Mm-hmm.
So then you write helium.
The end.
That's it, done. Now this next one. Oh, you know what we didn't do? We didn't put the numbers. That's why. That's okay though. Strontium-88.
38.
So if I find strontium right here is right here, 38. So I have to put the other number here. Krypton is a noble
36.
gas, so that's 36. 36. And PD is what, Mr. Sams? Where's
PD 46.
46. So this is 46. So if we add 88 and 84, we get 172. And so this adds up to 172, but I've already got 116 right here. So what's
56?
This will be 56, and this will be 38 and 36, 60, 74.
74, and then minus 46 is 28.
28. So now I'm going to look on my periodic table, find element number 28, and guess what the other chemical is? Nickel! It's the nickel van. Nickel noso. All right. Calcium is element 20. I happen to know that from my head. Californium, CM, is down here somewhere. 96. All right, I'm going too fast. Pause me, okay? And then SM. All right, I don't know what it is.
Samarium, I believe.
I think you're right. I don't know where samarium is. Oh, there, it's element 62. So the tops add up to 288, right?
Yep.
So 288 minus 147
141.
is 141. And then 116, did I do that right?
Yep.
Minus 62
54.
is 54. So we go look on our periodic table, find element 54,
Xenon.
and it's a xenon. See, you're just adding them up, guys. All right, now this one's a little tricky. Calcium is still element 20, and uranium is element 92. I just looked on my periodic table. Actually, I knew it in my head. And then zinc is 30. Now, the top of the left side adds up to 278,
Yep.
right? But we're going to subtract what?
70 and 4.
We have 4 neutrons kicking out, so minus this adds up to 74. So that's 204.
Yep.
But this lead. 92, 112. This adds up to 112 down here. Minus 30. It's 92, isn't it?
82.
82. It's lead still.
Yep.
Yeah. So that's the answer. This, folks, expect this on the multiple choice portion of the AP exam. You will see it, and they will give you one of these.
Yep.
It's easy. Just make sure the top adds and the bottom adds, and use your periodic table, which you'll have.
Yeah.
It's as simple as that.
Yep.
All right. Oh, yeah, we should just do some sample ones like this.
Yeah.
So if I have iridium 174, so if I find iridium is IR if I'm not mistaken. Iridium, actually, now as a side note, let me write this down. IR was 74?
77.
77?
Yep.
When I write 174, what does that mean?
That's its mass number.
So that's its mass number, which is 174. And if it goes via alpha particle decay, you have memorized those charts there. So that's a 4-2 alpha. You could also put an HE right there. And then we make them add up. But say you just need to know what this particle is, so you know it breaks into a 4-2 and plus whatever else. That'd be 170. And you lose 2 would be 75.
Yep,
So element 75 is RE. Found that from the periodic table. Now, if I decay a beta particle, well, platinum is PT. His number is 199, and his mass number, his atomic number, Mr.
78,
is 78. If he's going to do the beta particle thing, that's going to make a 0, a -1, beta, plus, that'll be 199, and then it'll go up. That's that one where it goes up 1.
Yep.
And 79, and that's gold.
Gold. Hey!
Ooh, we just made gold!
We turned the alchemist's dream.
Yeah,
right
we
there.
turned platinum into gold. The only problem, of course, is
I think platinum's more expensive.
Is
than gold,
more expensive
isn't it?
than gold.
Ah, darn it!
Positron emission. All right, so this is going to be sulfur, S31. Now, sulfur's number is like 12?
16.
16. One too far. 16. He's going to make a positron, so that's a 01E. So I just know my particles, right? From that other chart. That'll be 31 and
15.
15. Element 15
P.
is phosphorus. I don't need this line here. That's a mistake. All right, an electron capture for krypton. I'll do that up here. Krypton 76. That's krypton
36.
is 36.
It's got
And
to
it's
capture an
an
electron, so
a
it's a beta
0,
particle.
-1, E. So that's going to be 76 and 35, right?
It is, yeah. And 35 is bromine.
So that's the answer. This is easy, guys.
Yeah.
Just so easy.
Yeah.
All right, now let's
Uranium does this mess.
Now we also have some oddness in if you take a uranium-238 molecule, atom, whatever. Actually, isotope would be the term.
Yeah.
It actually undergoes an alpha particle decay, and then a beta particle decay, and then another beta particle decay, and then an alpha, and then a beta, and then an alpha, and then a beta particle. And eventually it turns into lead over like a billion years or something. So it's a very, very long period of time. But you can actually, well, let's just do one of those.
You want to do all of them?
Not really, because you can't really see it.
You kind of.
I think
we've
you got
gone
the
through it.
idea.
You,
Yeah,
you
you
get
got
the
the
picture.
All right.
Yeah.
All right, so we're going to skip that. All right, now, 18.2, though, second to last thing of the year.
Kinetics. Guys, remember kinetics?
You remember it? Yeah, and basically it follows what we call first-order kinetics. Remember, you used to write the natural log of A equals negative KT plus the natural log of A0. Well, guess what? That's the same thing that applies here. Actually, the equations are slightly rewritten.
Yeah, it's the same thing, it's just...
But now we're going to use, instead of, when we have radioactive things decay, we're going to use an N. Now the N stands for the number of nuclei.
Yeah.
But it is proportional to the mass of the object. So you can actually use mass. So it can be the number of nuclei or the mass. The N0 is the original amount, and the N is the amount at some time T.
Yes.
And the half-life is just this 0.693 over k. We've seen this before. And the rate equals k. And we used to write rate equals k, and we still will, for times a to the x power, right, or whatever. But this is first order, so it would always be to the first power.
Mm-hmm.
All right, so let's take a look at some examples.
Yeah.
Math is easy. All right, Titanium-99 used to form pictures of internal organs in the body to access heart damage. Hopefully this is not a problem we're going to have. All right, the rate constant
My dad had that done.
Oh, yeah. You did? They used titanium?
I would imagine.
Yeah.
That's the radioactive dye they stuck in his
So the
arms.
rate constant is this. So this is what? This is equal to k.
That's your k.
What's the half-life? Well, remember the half-life equation, T1/2 equals 0.693 over k. So in this case, that'll be 0.693 over 1.16 times 10 to the minus 1. So what do you get, Mr.
Well,
Sanders?
it helps to have your calculator actually turned on when you're punching numbers in.
Yeah.
Yeah, it took me a minute. Okay, there we go. 5.97 hours it would be. Because the unit for K was hours.
Yeah. Hours to the minus 1.
Hours to minus 1, right.
Okay, so now this one's a little different because it's going to say how much. So the half-life, they gave us the half-life, and we started with a 1 milligram sample after 335 hours. So we're going to use this equation. The natural log of n over n0 is equal to negative kt, because I have a time, 67 hours. That's actually the
That's
half-life.
the half-life. We're going to have to use that to find K.
And 335 is my time.
Yep.
So this is equal to t, but I need to find k. Now n0 is, this is n0.
Yeah.
All right, so let's find k. So k will be equal to 0.693 over the half-life. So that'll be 0.693 divided by 67. You get a pretty tiny number there.
0.0103.
So I'm just going to say the natural log of x over 1. X is my n, because I want to set this up.
And the
in my
1 is
solver.
from the 1.000
Yeah,
milligrams.
this is the 1 is from this. If this number is 72, you put 72, is equal to negative 0.0103 times 335. You can put it in your solver or not. For this one, you probably wouldn't need to, really.
Nah.
And so you get 0. So n is equal to 0.032 milligrams. So after 335 hours, you have 0.032 milligrams.
Yeah.
Now let me say something too on this. If you get the AP exam and you get a multiple choice question like this, the interesting thing that they will do is they will almost always give you a even number of half-lives. Does that make sense? And so hopefully I have a problem like that. If not, we're going to make one up.
Yeah,
All
I think
right.
there is one in here.
I think so. All right. Let's do another one. Woodcraft from a Chinese temple has a carbon-14 activity of 24.9 counts per minute as compared to 32 at standard 0H.
Yeah, now you said that the number of nuclei was proportional to the mass, but it's also proportional to the
number of-
activity in the Geiger counter.
So basically this is n, and this is
And
n0.
zero.
And I think we're going to solve for time.
Yeah, because it wants to know...
Yeah, half-life. Yeah, some old temple thing.
Yeah,
Wooden
determine the
artifact.
age. How old is it? Yep.
So we're using the same equation. We're going to use the natural log of n over n0 is equal to negative kt. So we're going to just solve for t now. So the natural log of n today is 24.9. N a long time ago was 32.5. I never have figured out how they knew that, by the way. How do they know that? 5,000 years ago, they didn't have a Geiger counter. I don't know. There's somehow that these guys know
No, it's
this.
based on what the activity of a living organism would be today versus something that has died and then is no longer going through that. It's no longer replenishing the carbon with the carbon dioxide from the air.
I knew that. Okay,
Yeah.
something like that. All right, and K, we got to do K. K is going to be the 0.693 divided by the half-life, which they said was 5,715 years. So this will be a pretty tiny number.
5, 7, 6, 5. Boom. 1.2 times 10 to the negative 4.
Solve for T. So what is this term here, Mr. Sams? We'll work it out. What is this term here equal to? The
which?
log term.
0.766.
0.766 would be equal
Oh,
to...
sorry, log of 0.766, which is negative 0.266.
So negative 0.266 would be equal to negative 1.2 times 10 to the minus fourth times t. Divide both sides by negative 1.2 times 10 to the minus fourth.
Yep.
Negative 1.2 times 10 to the minus fourth, and you get t to be what?
2220.
2,220, and that's years.
That's years from present.
Right. Yeah, so this piece
how
of
old it is.
wood,
Yeah.
when that wood died,
Yep.
not necessarily when they made the artifact,
Right.
it was 2,220 years ago.
Yep.
Okay. All right. We should probably do one of those even half-life problems. Don't you
Yeah,
think, Mr. Sims?
yeah.
So this would be a sample question. This actually tends to appear in the multiple choice section of the
Yeah.
AP exam. Now, a lot of you would think, oh, I've got to do natural log of n over n0, and it would work.
Yeah.
But the good news about this one is that we have 8 days and we have 32 days for half-lives.
Yeah.
So if I start with 100-gram sample, I like to do it like in a chart.
Mm-hmm.
This is the mass, and this is the time. So at 100-gram sample, that would be at day 0,
Right.
And then if I go to 8 days.
8 days. That's one half-life.
One
is 8
half-life,
days.
of course, there will be 50 grams. And if then I go to 16 days, I keep adding
That's
8.
2 half-lives.
That will be 25 grams.
Hmm?
And if I then go to 24, there will be half of this again,
Right, 3
12.5 grams. You just
Yep.
keep cutting in half.
Mhm.
And at 32, there would be half of that would be 6 1/4, right?
There it is. So
That's
it's 4
easy.
half-lives from the original, so you just cut it in half 4 times.
Yeah, you might just say, oh, 32 divided by 8, that's 4. And then you figure out it's the fourth half-life. 1, 2, 3, 4. Watch that. You do have a 0 half-life, too, so you don't want to
Right.
get the third one when you should have the fourth one.
And that will be one of the choices, guaranteed.
Yeah, yes, yeah, exactly. So watch that. It's tricky, but if it's a multiple choice question with half-lives, just make a little chart, and boom, you're going to have this answer in, well, what, about a minute, probably.
Or less.
Or less, yeah. Okay, how do we use radioactivity? What's the point? What do we use? What do we use to detect it?
Well, we detect it with the Geiger counter. And that just detects the alpha particles or the beta particles that are coming off of a decomposing.
Yeah, so
compound.
we have these devices that can measure radioactivity. You might have seen it in the movies
Yeah.
and stuff like that. Yeah.
They
Tick, tick,
chirp.
tick, 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 tick. Yeah.
Yeah.
Okay. There's a number of I got 4 things that we use we use nuclear stuff for. We use it for old things.
Yep.
Well,
Just the example we just did.
yeah, the carbon-14 dating. You can date an old artifact from and say this was the wood died 5,000 years ago or 2,000 years ago or whatever it might be. Also, there's some medical uses for radioactivity.
Yep. So like radioactive dyes for, like we were talking about earlier, detecting heart blockage. So
Yeah.
when my dad went in to get his heart checked out, they injected him with this dye, and then they hooked him up to an X-ray machine. They could see where that dye stopped in his heart. There was some blockage there, and they had to go in and
but
open
why
it up.
would they use radioactivity? Why didn't they? I mean, why do they use that? It sounds kind of dangerous to put radioactive stuff in someone's
It
body.
does, but it provides contrast between your non-radioactive parts that are in
Yeah.
there. And
Actually,
then
yeah.
they use things with really short half-lives too, so it's decomposed and out of your body within a few days.
Yeah, one thing also that's very cool about radioactive things is they can be detected in infinitesimally small amounts with Geiger counters. Now, some of those Geiger counters are pointed at somebody's body, essentially. Not exactly a Geiger counter, but basically it's
A detector
a
of some
detector
sort,
of some sort. It can be detected at such small amounts. So that's something that's very cool about it. And then they can find blockages. When my mom was really sick, she had cancer, and she had they gave her some barium treatments to discover where some blockages were in her intestinal system.
Oh, I've had that before, actually. I had to drink the barium milkshake.
Yeah, the barium milkshake, and they take pictures as it goes down. And
Upper GI,
Well,
not fun.
unfortunately, she had the reverse, the
Oh,
lower GI.
Yeah.
Yeah.
And then they put you on a table, so after you've drunk this nasty milkshake, they put you on a table and they rock you around in a bunch of different
Nasty.
orientations,
Oh.
and it's not pleasant.
Energy is interesting, of course.
Yeah.
This is becoming a bigger issue. I just saw that the nuclear energy industry just, you may be watching this years later, but the nuclear energy industry is hiring tons of people in our down economy because a bunch of nuclear power plants are about to come on board so that you can have power plants. And then lastly, they can be used, sadly, for weapons, and they're very, very destructive. Let's talk a little bit about a couple of these. Nuclear energy. Basically, you have the nuclear reaction. This is a schematic of a nuclear power plant. These are the things that are being built, a number of these. We could go into details of it's somewhat controversial. But
It makes steam.
basically, they have this reactor,
That's the point.
and they have the nuclear chemicals. It actually does fission,
Yep.
and what happens is it heats up a bunch of water. The water then pumps through goes out here, and it pumps through another thing so that this container right here never comes into contact with something that goes out in the world.
Right.
It then boils water. The water turns into steam. It then turns a steam turbine, and you make electricity.
Yep.
They then cool that water, send it back. It's just this loop. You got like several loops happening.
By the exact same process is used in a coal-fired power plant,
yes.
but the source of the heat in a coal-fired power plant is burning coal. The source of the heat in a nuclear power plant is the nuclear reaction.
And one thing that's so nice about nuclear power is that you can use
controllable.
a very that's true, but it's also you can use a very, very small amount of material to get a very large amount of energy.
Yeah. So the only problem with nuclear power is you've got a waste product when you're done that you have to do something with.
But it's a very, very small amount of waste product.
That's
and there's
true.
No greenhouse gases.
Exactly, no greenhouse gas. So yeah, from a greenhouse standpoint, it's very, very clean.
So a lot of people really think nuclear power is a great opportunity or option for the world's power. Many other countries than the United States use it almost exclusively for their electricity.
See, my brother and my dad are coal miners, so I can't.
So
I can't say I like nuclear power because they'll get mad at me. But I think it's a very good option.
I think it's a really good idea, actually.
idea.
Okay. Now, why do scientists get so excited about all this nuclear stuff?
Because it's neat.
No, it's because it's
the last podcast.
No, it's because it's lots of energy.
Oh, okay.
Because if you think about it for a moment, this is actually the interesting thing about nuclear. This is what gets them kind of all jazzed up. If you were to take the mass of a proton, this right here is the mass of a proton.
Yes, because it's...
And this is the mass of a neutron.
Yeah.
But if you were to look at an oxygen atom and find out the mass of the nucleus of an oxygen atom, it would be 8 of these. So let's actually do the math on this, Mr.
Okay.
Sams. So if I take 8 protons, so 8 times 1.6726 times 10 to the minus 27th, plus
2, I'm going to include that last digit in there.
62. Yeah, you should do the whole thing. Actually, I did 262, yeah. And then we took 8 times 1.67493 times 10 to the minus 27th. And we added those up, we would get what? Mr. Sams is busily typing, trying to figure out how to do this in his computer.
Whoops, I just screwed something up.
All right.
Put the plus sign in the wrong spot in the parentheses. Ah!
All right, after much derivation, Mr. Sams actually added it up. It is what, Mr. Sams?
2.67804 times 10 to the negative 26th.
Now,
I'm actually going to go back and double check my work, but I think
that looks right. Now, this is the mass of 8 protons and 8 neutrons. But if you actually weigh a nucleus of oxygen, guess what you get? 2.65.
Less.
Instead of 2.67. Wait a second. I thought if I take two things and I mix them together, and like if you and I stood on a scale individually,
yep,
and then we stood on the scale together,
yep,
we would weigh the same as the sum, right?
Exactly.
But the interesting thing is when you take the protons and the neutrons and you add them together, they weigh more than the actual nucleus. So when this atom forms, it loses mass. In fact, we have a name for that. It is called the mass defect. Everybody write mass defect. There's a lost amount of mass. That lost amount of mass, we would actually, let's find, what is the lost amount of mass? If you subtract these two numbers, 2.678704 minus 2.65535.
So 2.65535. We get 2.3354 times 10 to the negative 28.
So you lose 2.3, whatever, times 10 to the minus 28 kilograms. What happens to that mass?
It deposits itself on my love handles.
No.
Oh.
It is converted to energy. All right. Oops, it's called the mass defect. All right. So we have, let's look at our number here. And actually this utilizes an equation. This is a very famous equation. You might know this.
Yes.
E equals mc squared. Einstein's important equation. So it's actually, as a side note, it's not actually E equals mc squared. It's E equals delta mc squared, the change in the mass.
Oh.
Our change in mass was 2 point what?
I don't remember.
2.33 times 10 to the minus 28th. By the way, the m does have to be in kilograms.
Yep.
Times c is the speed of light, which is 3.0, times 10 to the 8th meters per second. But you not only do you take that number, which is a big fast
Square
number,
it.
but you square it, and you get how many?
You get 2.10 times 10 to the negative 11th joules. I believe it's joules, yeah?
Yeah, that's joules.
That's
now,
joules per
atom. So if we were to have a mole of those atoms, you would times this by 6.02 times 10 to the 23rd
Yep.
atoms in a mole.
And you get 1.27 times 10 to the 13th joules.
That's joules, and if we divide that by 1,000,
1.26 or 1.27 times 10 to the times 10 to the 10th.
and that's
Kilojoules.
kilojoules. Now the reason
That's
I do
per
this,
mole of
that's per
oxygen.
mole. If you were to burn methane, this is natural gas that we get out of the ground. It's 882 kilojoules per mole. How much more would you get out of this? Take this number, Mr. Sams,
Okay.
and divide it by 882. I think it's about a million.
82. It's
1.4 million?
3, 4, 5, 6. It's 14 million.
14 million. Now what I want to say is that if I had 1 mole of oxygen that I could smoosh together using nuclear chemistry, and I had 1 mole of methane, I would get 14 million times more energy out of the nuclear stuff per mole.
Wow.
That's a lot. So if you think of your coal mining family, no offense, but if I had a ton of coal, 2,000 pounds of coal, I would need 14 million times less nuclear stuff to get the same amount of energy.
Yep.
So take a ton, divide it by 14 million, and you've got just a itsy bitsy little piece to get the same amount of energy. This gets scientists like going, like, whoa, that's just amazing. Energy is a huge problem in the world. You can get a lot of energy out of nuclear stuff. All right. Now,
All right.
when the nuclear is happening, there are 2 varieties of processes that occur. One is called fission. What is fission?
It has to do with fish.
Like fish.
Fish.
Yeah, like when you go fly fishing. No, it does
Oh,
not.
sorry.
It is when large nuclei
Break up.
break up. So an example here would be uranium-235. This is actually the stuff that makes nuclear bombs. And it breaks apart actually after you add a neutron into 2 fission fragments and eventually turn into, we didn't explain, but 2 smaller nuclei.
Yep.
Those nuclei then produce a neutron. This is actually something else, but
Yeah.
but it is. It breaks apart into smaller nuclei. And then fusion is a little bit different. This is when small nuclei join
They fuse
or
together.
fuse together.
This is what happens in the sun.
Right, so we have deuterium, hydrogen, which weighs 2, mixed with the tritium. They combine and they make a helium, and they kick off a neutron. And also, they lose a little mass, and when they lose that little bit of mass, lots and lots and lots of energy. All right, we're almost done.
We are.
How do you build a nuclear bomb?
I don't know, but I bet you're going to tell us.
Yeah, nuclear bombs. Sad to say. A horrible thing that mankind has invented, no question. Lots of interesting history about the nuclear bomb. You ought to read about that someday. The Manhattan Project and Einstein and Oppenheimer and the whole group. All right, back in the 1940s. First of all, there's this thing called a chain reaction. What's a chain reaction?
A reaction that causes another reaction to happen right after it.
So, all right. So a chain reaction is a self-sustaining fission process. Now, if you have subcritical. Let's define these terms and then we'll explain the whole bomb thing. What's a subcritical?
That's when we've got less than 1 neutron causing another fission event.
And critical?
That's when we have exactly 1 neutron
1 neutron per event.
per event, and then producing again another neutron.
To produce, yeah. We'll illustrate this.
Right.
Another neutron.
So it's just kind of sustaining itself there.
Yeah, and supercritical.
Supercritical is when more than 1 neutron from each event causes more and more reactions. So if you have a nuclear event occurring that was started by 1 neutron and it kicks out, say, 3 neutrons, then we're supercritical.
And actually, when you have a nuclear power plant, everybody gets worried that somehow a nuclear power plant would blow up. But they always have subcritical amounts of fissionable material.
Right.
So it cannot blow up. Now, it could melt down,
Right.
but it cannot blow up. Okay, so watch that. Now, a bomb, on the other hand, of course, is where we
They're shooting
move.
for supercritical.
They're shooting for supercritical. So here's actually that picture we saw a minute ago. If I have a neutron that bombards a uranium-235 nucleus, it will split apart into two other elements. I think it's barium and something else.
Something else.
Actually, it's on here.
Barium and krypton.
Barium and krypton. So it makes barium, and then let's say this is krypton. But then it kicks out three more neutrons in the reaction.
So at that stage, we're talking supercritical reaction.
Because then if you've got another uranium-235 atom close by, it will then strike this nucleus, and he will make 3. And he will make 3. So it goes from like 1 to 3 to 9 to 27 to 84.
Whatever, 27.
7 times 3 is 21, 81, etc. But it happens in milliseconds or microseconds or whatever, and it can happen extremely quickly. So if you want to have it to be supercritical, this is a picture of a supercritical, then you can get it all going. Essentially, when you build a nuclear bomb, all you have to do is get the right amount of mass of uranium-235 together, bombard it with some neutrons, and it blows up. Now, how do they do that? Okay, there are actually two designs. There's the gun type method, and there is the implosion method. I forget what they call it.
Yeah, implosion.
Implosion. There, it kind of gets right there. I can't even read. So then the gun type, basically, you have the subcritical uranium-235, and then you got some chemical explosive, and they have to bring them together at exactly the right time. And once they get together at exactly the right time,
you now have a supercritical mass.
And then it blows up.
Yep.
And so you can either kind of draw them all together into the center, or you can get them to have sort of a gun design. And they both have been designed, and it gets just, and then this is what you see happen. Kablooey. Yeah. And so they've got some regular explosive TNT we talked about in the last podcast. That's what they use. And they can get it all together. Yeah, I'm pretty sure it's TNT. Yeah. Now, we should also make a note that those were, what we just saw, this subcritical, supercritical, these are for fission bombs.
Yeah.
Or actually usually called an atomic bomb. Sadly to say, we figured out a better way to make a nuclear bomb. There's what we call a hydrogen bond. Bomb. I said bond, didn't I?
You did.
In a hydrogen bond, they use nuclear fusion. And we didn't really talk about this, but nuclear fusion has a lot more energy than nuclear fission. So remember that 14 million times? It's much worse than that. That's a lot of energy.
Fusion, wasn't it? The 14 million?
Oh, that was 14
that was
million.
Fusion, yeah.
Yeah, fission is probably only 1 million. That's where I think I knew that. Okay. But anyways, like 14 times stronger. And so they have nuclear fusion. And actually, to get fusion to work, you actually have to use an atomic bomb
to get it really hot.
To get it hot enough to make it work.
Right.
Otherwise, it doesn't work. So they actually
we're talking like the sun temperatures here.
Yeah. So we could do that. Interesting story. Let me tell you a story about the nuclear bomb. It's just intriguing. Kind of a sad thing. In 1940s, when they were designing the bomb with the Manhattan Project, a group of scientists, and we were talking like the brightest scientists in the whole world.
The world.
Yeah, these guys were amazing. You know, I don't think Einstein was in the room, but guys like him. I understand that the vast majority of people had won Nobel Prizes. I mean, like, there were 8 Nobel Prize people in a room of 14 people. So amazingly brilliant guys. So they're in a room at, I believe it's Caltech or Berkeley, some university out in California, discussing the possibility of building this bomb. And they're discussing it, and then one young man who became famous later, but he was not a Nobel Prize winner. He got up and said, "Wait a second." And he said, "Wait a second." He went up to the chalkboard. "Can I have the chalk?" He said. This is before they had computers and projectors and all that. He went to the chalk and he did some math on the board, and he said, "If we were to blow this up, couldn't it set up a chain reaction and blow up the world?" So he got the chalk. He went up to the front of the room and he showed him the math. And everyone said, "Oh my gosh, it could happen." They all convened the meeting for the day, said, "We need to go think about this because we don't want to blow up the world." They came back the next day, they calculated the probability, said it was 1 chance in a million, and they went ahead with the project. But they really believed there was a chance, 1 in a million, that if they blew up a nuclear bomb, it would blow up the world. Turns out they were wrong. That was good. But it goes to show you these guys were very afraid of this, and they did the math, and I guess, It still, of course, has killed lots of people. By the way, the atomic bomb that blew up over in Japan, the only two that's ever been in Hiroshima and Nagasaki, that was the atomic bomb. The fusion bombs are much, much worse, like we said. They
Those have
tested
never
that.
been used in warfare, have they?
Never in warfare. They were tested on some islands in the Pacific. And you know what happened to those islands?
They blew up.
They blew up and they don't exist anymore. They totally
Annihilated.
vaporized
Yeah.
the island.
Wow.
It doesn't exist anymore.
Wow.
Since then, they've done underground tests because, of course, it creates
Got
fallout.
Tired
and,
of vaporizing islands. And
ve-
stuff.
and like causing cancer to animals and people and stuff too. Yeah.
All right.
Okay.
You know what?
My hat. Where'd my hat
Where's
go?
your hat?
I don't
Put
know.
your hat on.
There's my hat. Well, guys,
On
that
and done.
we're done. Sorry to end on such a negative note, but we are physically done with podcasting for LinkedIn or whatever for everything.
Yeah, this is it.
Done.
You've got all the stuff now. You need to review and study for the test, and we'll be doing that for quite some time.
Have a wonderful life.
Woohoo!
Rock.